Okay, good morning. Sat Sri Akal. Okay. All right, so today I'm teaching in the morning 2 times, and then Dr. Sogi is teaching in the afternoon. So in the first hour, what I'd like to do is give you an introduction to parameter estimation and talk to you about the most important aspect of the analysis, which is the scaled sensitivity coefficients and how to get them. And then the second hour, I have an example of some data it applies to food science, especially, where you can collect some data on the extraction efficiency, and you have a surface, and then you try to find the maximum, like a response surface example. Okay? So what I'd like to do is have us go beyond the black box. Does everybody understand when I say black box? You know black box? Black box means you don't know what's inside. You just run the program and get the results. But you don't know what's happening, so I want to avoid that. I would like to show you what's happening inside the black box. So let's start with the introduction to parameter estimation. And the book that I reference here is electronically. I downloaded it. I uploaded it to the Google Drive, so you can use the book if you want. So you can see the parameter estimation. It provides tools so you can use data. So number y. That's a forward problem. The inverse problem is what it sounds like. You're given the data, you don't know the parameters, and you estimate the parameters from the data using the model. So let me show you that. Here's an example, right? So forward problem, right? I give you m and b, you calculate y. The inverse problem is I give you a bunch of y data, and then you estimate the m and the b. So in Excel, they have a trend line, right? You can do a trend line, linear trend line, and it's estimating the parameters for you. Graduate student do most of the time in the research. If you're doing research, you're inside a lab, and you're doing what? You're collecting data, right? Okay, so think about this. When I go to a research conference and give some papers, or I'm reading a journal article, so I listen to the person who's giving the presentation, and the people almost never say this is a forward problem, this is an inverse problem. They just give the talk, and I have to figure out which one it is. How do you know how do you know that the researcher is working on an inverse problem or a forward problem or both? So I will tell you how. First of all, the researcher has to have a mathematical model. If there's no mathematical model, then it doesn't apply. This doesn't apply. If you have a mathematical model, here's how you know if it's a forward problem. It's a forward problem if no data are needed, and you're just generating simulated results. That's a forward problem. If it's an inverse problem, it requires data. You have to have data. Now, the data can be collected in the lab. It can be taken from other journal articles. It could even be generated by you in a simulated fashion with error. So you could generate perfect data, and then you could put some error in it, and that becomes a simulated data set. Then you can do the inverse problem on the simulated data set. But no matter what, an inverse problem always requires some data. Okay? So that's how you know. So when I'm listening to the talk, the person says, okay, I have a mathematical model, and then here are my results. And I think, well, okay, let me look at the results. Oh, he generated, this is just the y. Okay, that's a forward problem. Then they say, oh, and then I fit the data. Okay, that's an inverse problem. And then I validated the model. Oh, that's a forward problem. You see what I mean? They're jumping from forward to inverse to forward. And then so when I talk to you, I always tell you whether it's a forward problem or an inverse problem, so that you always know. Because the inverse problem is much more complicated than the forward problem, especially for a nonlinear problem. So let me show you that. Now, if you're wondering, let's see, I have it written here. Okay, So you've heard some people use COMSOL and Fluent. These are commercial modeling software. So when people tell you he works in modeling, what does that mean? I'll tell you what it means. 90%, 95% of the time, if somebody works in modeling, it means he does the forward problem. Okay? When you talk about me, I work on modeling. I don't do the forward problem. I almost never do it. I do almost all inverse problem. So that's why I tell you, my research is on the inverse problem. It's a huge difference. Huge. People who are using COMSOL and Fluent, they are almost always doing the forward problem because COMSOL and Fluent, ANSYS, it only does the forward problem, no inverse problem. So you don't need data. So I ask you, as a faculty member, as a graduate student, what are you doing in your research? Am I right that probably everybody in this room is collecting data? Is that right? Okay, how many people are collecting data? Show me by hand. Okay, the other people, you're not collecting any data? Is that right? Okay, who's not collecting data? I don't know how you, okay, so are you a graduate student? So are you doing simulation? Are you doing simulation or collecting? Okay, I can talk to you at the break. But most of the time, the graduate students are collecting data. The MATLAB is the brain. So the MATLAB feeds the guesses of the parameters, and then it lets the software COMSOL and Fluent, it runs, and it gives one answer. And then MATLAB compares the data to the one answer, gets a residual sum of squares, and then it sends a new set of parameter guesses back to MATLAB. Back to COMSOL. COMSOL generates another solution, and it comes back to MATLAB. So it's like this. MATLAB is changing the parameters, and COMSOL is generating different solutions. So MATLAB is doing the inverse problem, okay? And then you get a minimization of squares, and then you can stop at when you reach a certain tolerance level. So what I just told you shows you that to do the inverse problem, you have to know how to do the forward problem many times. Because the forward problem is being done many, many times, and every time it's done, you compare the forward problem results to the data, you get some kind of residual, sum of squares, something like that, and then you keep going until that residual reaches some minimum, and then when it gets to the minimum, you can stop. And those are your final parameter values. So that's the inverse problem, okay? Now here's a nice picture I took from the internet. Okay, yeah, let's see. Can I reduce this window? How do I reduce this window? Yeah, there you go. Okay, here it is. So look, on the left side is what everybody's familiar with, which is a forward problem. So you know your betas are at the top, and then you send them through a mathematical model, which is eta, and then you generate the etas. So my eta is the model. So you send your parameter values into the mathematical model one time, and you generate a bunch of etas, and you're finished. It's just one time, straight through. Okay. Forward problem is very different. On the inverse problem, you have to have some data. You send it through the mathematical model with parameter guesses. You generate one solution. You compare it to the data, and then you come back again with new. But in medical imaging, airport security, physics, astronomy, drilling for oil, it's all inverse problem because they're checking the bottom of the ocean and trying to find out the density. It's another example. The submarines, the bats, and the dolphins. They all use echolocation. So they send out a signal, they receive the signal, and they determine a location. That's an inverse problem. Everybody who works in medical imaging to find out where is the cancer in your body, that's an inverse problem, right? It goes around your body and it constructs your organs and checks for the cancer. That's all inverse problem. Okay, and then in food science, if you're doing, as I said, if you're doing the pigment, you're doing pigment and you want to optimize that. Okay, so let's keep going here. Now I want to give you an example. So, check here. Hold on a second. Yeah. Okay. I need to talk to you. So I'll tell you about the sensitivity coefficient. So first, right here, this one, that's the sensitivity coefficient. So I'll talk about this today. So the sensitivity coefficient is the partial. It's a derivative. So it's the partial of the model with respect to the parameter. So every parameter has its own sensitivity coefficient. And what it's doing is it's telling you how sensitive the model is to the parameter. If the model is not sensitive to the parameter, you can just remove the parameter. We don't need it. If the model is very sensitive to the parameter, it's easy to estimate, or it's much more accurate when you estimate it. I'll give you an example of that later. So let me help you on here. Oh, so let's do. Yeah. Okay. Now. We have to know, is the model linear or nonlinear with respect to the parameter? If the model is linear with respect to the parameter, then you do not need to iterate. You just go through one time and you get the answer of the parameters. If the model is nonlinear, you have to make a guess of the parameters and then iterate. Okay? So it's more complicated. So the first thing is, you need to know if the model is linear or nonlinear. So how do we do that? So the model is linear if all the sensitivity coefficients are not a function of the parameters. So let me help you how to do this. Okay, so if you take the derivative of the model with respect to the parameter, one of the parameters, and if you see the parameter on the right side, it's nonlinear. If you don't see the parameter, it's linear. Okay? So let's try that. All right. So I'll do the whiteboard too. So I have eta equals b plus m. Let's see. B plus m. Okay. So I'll help you. So this should be 1. And then and this one, the eta dm. Okay? I'll tell you what, let me do it another way. Okay, so on the first one, do you see, I'll say, is there a B? So right here, no iteration. Okay, let's try next one. So my question on the second one, is it linear or nonlinear? Linear. Linear, okay, good. Okay, okay, good. So what that means is you cannot estimate the m, but you can estimate the m squared. So if you do the problem, you can only estimate m squared. Okay? And then if you want the m, you have to take the square root of it. That's all that means, okay? All right. Let's keep going. Okay, how about this one? What's the, you know the derivative? Okay, so that's the derivative with respect to k, right? Minus at e to the minus kt. So linear or nonlinear? Nonlinear. So that means that you have to put in a guess for k and then do iteration. Okay, you have to do some iteration. You cannot just do one time through. And now if I take the log of both sides, so this one will be right? Okay, so linear or nonlinear? I heard both. It's linear because there's no log a and there's no k. So in other words, the sensitivity coefficient is not a function of the parameters. So it's linear, and that means you don't have to guess at the beginning. This is why people linearize the model using a logarithmic transform. You see? So in this one, you have to use iteration. In this one, you don't have to use iteration. So people use a logarithmic transform. But I can tell you that if you use a logarithmic transform, the result that you get for log a and for k can be slightly different from this one. It depends on your data. If your data variance is constant when you collect for this model, then the results will be very close. But if on this model, if you have an increasing variance as you collect your data, then you'll get a different answer. If your data look like that, you'll get a different answer. Transform. Well, I don't want to say that. What I mean is you should use this model, because this model assumes you have a constant variance. But anyway, the summary is, I don't usually do this. I usually just stick with my model as long as the variance is constant. Okay? We can talk about that more later. But my point is, these are actually two different models. Okay? That's what I'm telling you. All right. And, well, this is another model. Let's not, actually, something happened with my font. We'll get back to that one. I'll just show it to you. So you can see this model. This model, if you take if you do dA to dN, you end up with n on the right side. Okay? So it's a nonlinear model. The realogical model is nonlinear. Okay? So once again, if the variance is constant, then you probably get close results, okay? But if the variance is different, you'll get different results. Okay, so the only reason I was telling, the main reason was, if it's nonlinear, there's no, then as I've written, there's no analytical solution. You have to guess the parameters and then try and keep trying, okay? And so the MATLAB helps you with that. So then the question is right here. So you might say to me, but I use Excel and I get the result for the nonlinear models, like this one, and there's a log model, right? You've used it. You get a trend line, right? You've done the trend line in Excel. So how does Excel get the answer? Because it doesn't ask for a guess of your parameters. You know what it does? I checked. I went in and I looked at the manual for Excel. They logarithmically transform all their nonlinear models. That's what Excel does. So when you ask Excel for this, if you ask Excel for A and K, and it internally does this. If you want this answer, you have to go in and use Solver in Excel. Okay? Only Solver does that. Or you can do MATLAB, right? Which is what I'll show you. So that solves that one, okay? And then now, I want to get into the scaled sensitivity coefficients. So, let's see. I want to go to linear regression. How does Excel or MATLAB, how do they do linear regression? So we're going to use this, I'll use in the second hour. This is the multiple linear regression you can use in, yeah, question.
The value of A is increasing, but in the second case, A should be positive.
Okay, so your question is?
A can't be negative in the second equation. A can't be negative in the second equation, right? Because it's a log. So, but in first case, the value of A should be
solve for A by taking 10 to the power or E to the power. Okay? So just be clear on which model you're using. All right. So I want to talk about the linear regression, but in order to do that, I have to talk about your scaled sensitivity class. Okay, let me show you the scaled sensitivity coefficients, or actually, let me show you how to arrange them, okay? It's down on page 1. Okay, right here. First of all, this is something on my computer. In your notes, it's not like this. I should have done a PDF, but I forgot. Yeah, in the PDF it should be correct. I just use the PDF because font issue. Okay, sorry. Where did Okay, right here. Yeah, here's what I want to show you. Now, this is how we set up our linear model. This is how Excel does it and MATLAB. In fact, all the software does it like this. This is inside the software. So, your eta is the model, and the eta is going to be n by 1, where n, so n is the number of measurements, p is the number of parameters, and we're doing ordinary. Over here on the beta is p by 1. So if you have 2 parameters, it'll be 2. You know, beta 1, beta 2. That's it. It could be more than that, all right? Now, how do you get this sensitivity matrix? So every column is connected to a parameter. So for this first column, it's just the sensitivity coefficient for parameter 1. So you just do So here's how you set it up. Okay, so you have one column for each parameter, and you have one row for each data point. That's it. So then this goes. Okay, so that's why the sensitivity matrix is always n by p. N is the number of data, p is the number of parameters. Okay? And then I don't have time to go through this, but they just set up the sum of squares like this, like you see up there, sum of squares. And if you go through the math, you end up with this solution. So this is a solution for a linear model. So this is inside the Excel and inside the MATLAB software. So it does the x transpose x, takes the inverse, multiplies by x transpose times y. That's the answer, and it gives you all your parameters. Okay? So that's how you set up your sensitivity matrix for a linear problem. All right? It's just a recipe. Very straightforward. Okay? Now, okay, so what is the problem? The potential problem is if any one column is linear proportional to another, you cannot estimate those parameters. So if one parameter and another parameter give the same sensitivity to the model, you cannot separate the two parameters. Okay? So let me show you something. And then I'll show you how to set it up. Let's see. Okay, let's do... now I want to go to the regress. So let's do the regress, and I'll show you how to do regress. And now it'll make more sense. Okay, here's regress. So you have regress. Everybody see regress on the right side. So you do regress, and you do y. You put in all your y values, and then comma, and then your x. But your x is the sensitivity matrix. And I'll show you how to do that. On the left side is all your output. So you get b as your parameter. Your b interval is telling you your 95% confidence interval. Okay? And then your r is your residual. Your r is the interval for the residuals. And then the stats, I'll tell you the stats is per number. Now I want to show you, let's see, 1045. Okay, let me show you an example of how to do this. Okay, so I gave you a linear model, right? So now let's set up the sensitivity matrix. So we'll do okay, so what is that? D eta, D beta 0 is what? 1. What's that one? Just x, right? Finished. I just wrote the sensitivity matrix for that model. Right? So if you have 10 data, it's 10 rows. And only 2 columns because it's 2 parameters. Okay? That's your sensitivity matrix. Now, so what if I have a surface of x and y? So if you take, let's do the sensitivity matrix. Okay, beta 0, same thing, right? For this, beta 1. Beta 2. Beta 3. Beta 4. Beta 5. So those are the derivatives, right? It's just a derivative. So, and by the way, when I took the derivative, is it linear or nonlinear? Yeah. Why is it linear? You don't see any of the betas. There are no betas, right? No betas in the derivatives. So what I'm pointing out to you is, be careful about linear versus nonlinear. Some of you might be thinking this. So let's say that's an x squared, right? So you look at that and you say, wait a minute, the line looks curved. Isn't that nonlinear? It's nonlinear with respect to x. It's nonlinear with respect to x. It's linear with respect to betas. Does everybody understand that? This model, can you see it? This model is nonlinear with respect to x. We're not interested in that. We're interested in whether it's linear or nonlinear with respect to the betas. So with respect to the betas, it's linear. Right? We don't care if it's nonlinear with respect to x, because we're not trying to find x, we're trying to find beta. Okay? Does that make sense? Okay? So, polynomial models are all linear. Polynomial models are all linear with respect to the betas. All right? So, now here it is. This is my x. So, 1, 2, 3, 4, 5, 6. 6 columns. Right? Okay, so let's see. I'm having a hard time showing this. Okay. So I'm going to set up my data for you. A second. By the way, you can just run through each cell, one cell by one cell by one cell. So I can push run in advance, and it just goes one cell, and it waits for me. So if I go like that, run. So what it's doing is it's setting up some data for me. Okay, and then now, because if you give me the data, I can use it, okay? But I didn't have your data, so I had to create my own data, okay? So don't worry about that. I just created my data. Student, you're inside the lab, you collect your data. So here's the X and here's the Y. So you can help me on that. Maybe view, camera toolbar, click on this one, which is orbit camera. So we need to do the inverse problem. But I hope it's a linear model, then I don't have to do any iteration. Okay? So let's close this, and now we get into that part. So here's my linear regression. So now I want you to work with me on this. So linear regression. Now I use XF because I don't want to confuse it with MATLAB. So when I say XF, that's just my name for the sensitivity matrix. Okay, so don't worry about that. So now let's look at the board. What does it tell me? I set this up from this. First column, all ones, right? So what do I have? Right here, ones, and I have n samples, whatever n samples is 40, okay, I have a lot of data. See? 441 data. Okay, don't worry about that. I'm just making an example. So I have 441 data. So I need 441 ones. X times Y. X times Y. Now, what I want you to notice is I always put a dot here. See that dot? that tells you don't do matrix multiplication, just do cell by cell multiplication. First one times first one, okay? And the same thing here, xp times yp, you always put a dot and then multiply cell by cell, cell by cell, cell by cell, okay? It's just multiplying. So first I want to make sure, did you understand how I set up the sensitivity matrix? I set it up, okay? Because when you go here, right here, you see, let me do regress. Yeah, here's regress. So this is the preferred linear regression. You must add in a column of ones in the first column of x because of that. Because my first parameter is always the intercept, beta naught, okay? So that's why I put right here, beta 1 is, or beta naught, beta 1. By the way, in MATLAB, they don't allow you to use 0 for an index, so you have to call it beta 1. Sorry about that. So beta 1 is the intercept, beta 2 is the slope. Okay? So let's get back to the example. We're almost done on this. So if you understand, I set up my sensitivity matrix, right? And then, okay, and then my statistics, right? So let's run it. I'm going to do run in advance. Okay, let's look at my answers. So here are my answers. So my betas are, right, you can see 3.5 and so on. That's the intercept. Okay, now how do I know that they're significant? The way you know that they're significant is if the 95, first of all, it's if the p-value is less than 0.05. It's significant, right? The other way of saying that is if the p-value is less than 0.05, then the confidence interval will have the same sign, or I could say it this way, the confidence interval will not contain 0. So if the confidence interval contains 0,